In 10.1, we looked at permutations, which is a way of selecting some number of objects from a group of objects where the order matters. The order that you pick those things matters. So something like a race, if we have, one of the examples in the last lesson was you have 10 teams in a race, and you want to know the number of ways that you can have teams win first, second, and third. The order of those matters. It matters who gets first, it matters who gets second, it matters who gets third. In this lesson, we're going to be looking at combinations. So combinations is essentially the same thing, but the order does not matter. So we're going to be looking at something like, say, drawing 5 cards off the top of the deck and having that in your hand. So if you do that, if I draw 5, 1, 2, 3, 4, 5 cards off the top of the deck and say this is my hand of cards, well, the order of these cards doesn't matter. If we're, say, playing a game, I can mix these up, and it's still the same hand. The order that I put these in does not change what cards I have in my hand. So in this case, the order does not matter. So what we do in order to calculate this, well, there is a formula, but much like with permutations, I don't much care for the formula. I think it's messy and confusing. I prefer to just work it out. So you're welcome to use the formula if you want. There it is for your use, but I'm going to calculate these out by hand. All right, example 1. A standard deck of 52 playing cards has 4 suits with 13 different cards in each suit. Now, I did make a video that describes and shows what all is in a deck of cards. I'm going to assume in this lesson that you know the contents of a deck of cards, so if you do not, you need to go watch that video and make sure that you understand what's in a deck of cards. All right, part A. How many different ways are there to draw a 5-card hand from the deck if the order of the cards does not matter? And actually, the order of the cards is not going to matter for all of these as we work through them. So we've got 5 cards. I want to draw 5 cards. 1, 2, 3, 4, 5. So I'm going to put 5 spots there for the 5 different cards that I can have. Now, again, like I said, we're going to calculate the permutation first and then do something with that to get the combination. So let's pretend that I do care about the order of these cards. Well, then it's going to be just like last lesson. So for the first card, I can pick any of the 52 cards in the deck. Once I've picked one of them, there's only 51 of them left for the second card. And once I pick 2 of them, there's only 50 left for the third card, 49 left for the fourth card, and 48 left for the fifth card. And then I can count this up just by multiplying all of these together. And if you do that, you're going to get about 311,875,200, or exactly 311,875,200. Now, this is if the order of those cards matters. So if I don't care what order these cards are in, I'm going to need to divide by the number of ways to arrange those 5 cards. So in last lesson, we learned that if you want to know how many ways there are to arrange some number of objects, you just take that number factorial. So if there's 5 cards, then I can divide by 5 factorial. So that's 5 times 4 times 3 times 2 times 1. That will tell me how many ways there are to arrange those 5 cards. And since I don't care about the order, I need to divide off 5 factorial. 5 factorial is 120. And so if we multiply that out, we're going to get 259,896,0. So about 2.5 million different ways to arrange, or 2.5 million different ways to draw 5 cards off of the deck if the order of those cards does not matter. All right, part B. We're actually going to change this not just to the same color, but specifically black. It's a little bit easier to calculate that than if it's just could be either color. Okay, so how many different ways are there to draw a 5-card hand of all black cards? So again, I've got 5 spots. For the first spot, I could have any one of the black cards. So half of the deck is black. We've got the spades and the clubs are black. So there's 26 black cards. So I've got 26 options for the first card, 25 options for the next one, 24 for the next, 23 for the next, and then 22 for the next one. Multiply all of those together to get the total number of ways. And that's going to be 7893600. So almost 8 million. But again, this is the number of ways to arrange them, to draw them if the order matters. So if I don't care about the order, what I'm going to need to do is take this and divide by the number of ways to arrange 5 cards, which again is 5 factorial. So we take that nearly 8 million divided by 5 factorial, which is 120, and you get 65,780. All right, parts C and D, we're going to be looking at multiple events. So actually, if you look at the bottom, it tells you what to do in each of these cases. So if I'm looking at drawing 3 cards and 4 red cards, we're going to compare that to drawing 3 cards or black cards or 4 red cards. So these calculations are going to be very similar, but there's one minute difference. So if we are talking about having one event and the other one happening, so we want both of those to happen. I want to draw 3 black cards and draw 4 red cards. What we're going to do is multiply those together. If we're talking about or, if I could have either 3 black cards or 4 red cards, then we're going to add those two numbers together. So the setup is going to be mostly the same, except in part C, we're going to have multiplication, and in part D, we're going to have addition. But let's take each of these separately. So let's take 3 black cards first. So I've got 3 spots here. So for the first black card I choose, I've got 26 options for that, because there's 26 black cards in the deck. And then 25 options for the next one, 24 options for the next one. Multiply those together. And then we also need to divide by the number of ways to arrange 3 cards. So since I don't care what order these 3 cards are in, I need to divide by the number of ways to arrange 3 cards, which is 3 factorial. So that's 3 times 2 times 1. Work that out and you get 2600. Then for the red cards, we've got 4 cards that we need to be read. For the first red card, I've got 26 options. Once I've taken one of those, I've got 25 options for the next one, 24 for the next, and 23 for the next. Multiply all these together to get the total number of ways. And then since this is a combination, not a permutation, again, we need to divide by the number of ways to arrange 4 cards, because I don't care what order they're in, so we need to divide by 4 factorial. Work that out and you get 14,950. Now, like I said, if we're talking about drawing 3 black cards and 4 red cards, we want both of these things to happen. We're going to have to multiply these numbers together to get that. And if you multiply those together, you get 38,870,000 flat. Now for this part, if we're talking about drawing 3 black cards or 4 red cards, we can have one or the other. We don't care which one happens. So for that, we're going to take the total number of ways that you can draw 3 black cards and the total number of ways that you can draw 4 red cards and add those together rather than multiplying them. So the first bit here, I'm not going to bother writing all that out, but it was 2,600. The second bit, again, I'm not going to bother writing all that out. It was 14,950. And so if we have or, we're going to add those together and we get 17,550. We're going to look at a mathematical object invented or discovered maybe by Blaise Pascal, who's a scientist and mathematician. And you may have heard of Pascal in science classes because there's a unit of pressure named after him. So Pascal is a pressure unit. And he invented, being a mathematician that he was, he invented or discovered, maybe if you want to call it that, this triangle. We call it Pascal's triangle. So let's first talk about how to build this triangle, and then I'll show you how it relates to combinations. So we start at the top with 1. And then we're always going to be writing 1s down the sides. But then what you do, so again, we've got 1s on the sides, and then what we're going to do is actually add the 2 above each spot. So if we add 1 and 1, we get 2. So this row is 1, 2, 1. Then again, put a 1 on the outside, and then we're going to add these 2 together. 1 and 2 makes 3. 2 and 1 makes 3. And then put a 1 on the outside. The next row, start with 1. Then we're going to add 1 and 3, we get 4. 3 and 3 makes 6, 3 and 1 makes 4, and then 1 on the outside. And we'll keep going, put a 1 on the outside. 1 and 4 makes 5, 4 and 6 makes 10, 6 and 4 makes 10, 4 and 1 makes 5, and then put a 1 on the outside. And we'll do one more row. We can keep doing this. You can do it indefinitely, but we'll just do one more row. 1 plus 5 is 6, 5 plus 10 is 15, 10 plus 10 is 20, 10 plus 5 is 15, 5 plus 1 is 6, and then put a 1 on the outside. And again, we could keep going indefinitely. There's really no end to this triangle. We could keep going, but we'll cut it off there. Now, we're going to label these rows. So the first row I'm going to label as the 0th row. Second I'm going to label as the first row, and then second row, third row, fourth row, fifth row, and then sixth row. And then for the spot of each row, actually we're going to also start with 0, start counting with 0. So this is the 0th spot, first spot, second spot, third spot, fourth, fifth, and sixth spot. Now, the reason that we're going to start with 0 counting is because of how this relates to combinations. So if we start counting with 0 for the rows and the spot in each one, we can actually use Pascal's triangle to figure out combinations. Let's hold off on that for just one moment, because I want to point out that there's a lot of patterns in Pascal's triangle. This is actually quite a mathematical marvel, because there's just ridiculous patterns found within this triangle. And if you spend some time looking at it, you'll start to see some of the patterns. So for example, you can see a pattern here where we've got just the integers being added together. We've got all sorts of patterns in here if you keep looking at it. So I'll actually just let you take a look at that, see if you can find some more patterns in there, because there's quite a lot of really interesting patterns within this triangle. We'll leave that for you to look at. Example 2, let's look at trying to use this for combinations. So if we are trying to, let's read the problem here. There's 6 members of a Model UN club. We need to choose 2 representatives to attend a state convention. How many combinations of 2 members could be chosen? So this is a combination. We're choosing 2 people out of a group of 6. And so we can actually use these numbers then in Pascal's triangle to find the combination. So this is 6 choose 2. So if you go to the 6th row and then go into, that will actually tell us the combination. So go to the 6th row, which is the last one here. Go into, so this is 0, 1, 2. 15 is the number we're looking for. This is 15 ways to choose that. And just to check and make sure that this really did work, normally how we would calculate this, we've got 2 spots. For the first one, we could choose any of the 6 members. For the second one, we've got 5 members left. Multiply those together. And then again, since the order does not matter, it doesn't matter which order we choose these in. So it's just 2 people that we're choosing. We don't care which one's first and which one's second. All that matters is that there's 2 people. So we divide by the number of ways to arrange those 2 people, which is 2 factorial. So you get 30 divided by 2, which is 15. So you can use Pascal's triangle. If you don't like doing the calculations for combinations, you can use Pascal's triangle to do that.